So in today's pre-lecture, we're going to be introducing finite fields at long last. So recall from last time we defined f adjoint x mod a polynomial m of x. So in this thing, every polynomial is congruent to a polynomial of degree less than the degree of that modulus polynomial m of x. And we can define addition and multiplication inside of here. And I'm sure you won't be surprised to find out that it turns out that this is a ring. So it satisfies all of those ring axioms with the addition and multiplication that we talked about on Monday. So the question for today is, when is this ring actually a field? So that's what we're going to be looking at. So let's start by looking at z mod 2 adjoint x mod the polynomial x squared. So since everything in here will be congruent to something of degree less than 2, we can think of this as being the set containing 0, 1, x, and x plus 1. Since these are the polynomials in z mod 2 adjoint x with degree less than 2. So now let's write out addition and multiplication tables for this ring to see what the structure of these operations looks like. So for 0 plus 0, we get 0, 0 plus 1 is 1, 0 plus x is x, 0 plus x plus 1 is x plus 1, 1 plus 0 is 1, 1 plus 1 is 2, which is congruent to 0, 1 plus x is x plus 1, 1 plus x plus 1 is x plus 2, which is x over z mod 2. X plus 0 is x, x plus 1 is x plus 1, x plus x is 0, x plus x plus 1 is 1, x plus 1 plus 0 is x plus 1, x plus 1 plus 1 is x, x plus 1 plus x is 1, and x plus 1 plus x plus 1 is 0. So then for the multiplication table, everything 0 times anything is going to be 0, so we can fill those in. Then 1 times 0 is 0, 1 times 1 is 1, 1 times x is x, 1 times x plus 1 is x plus 1, x times 0 is 0, x times 1 is x times x is x squared, which is congruent to 0, so we get 0 there. And then x times x plus 1, we'd have x squared plus x, but since x squared is congruent to 0, we have x there. Then x plus 1 times 0 is 0, x plus 1 times 1 is x plus 1, x plus 1 times x is x, and x plus 1 times x plus 1, we'd have x squared plus 2x plus 1, which is congruent to 1 in this ring. So to decide if this is a field, we want to look and see if, based on our multiplication table, it satisfies those extra properties. What's missing is if you look at the things that we get when we multiply x by different stuff, we never get 1 there. So that means that x does not have a multiplicative inverse. So it can't be a field. For how many elements it has, we can see we've got 4 elements listed here. So that's got 4 elements. It's a ring with 4 elements. Now let's look at another example here. So once again, we've got a polynomial of degree 2 in z mod 2 adjoint x. So we can think of this as being 0, 1, x, and x plus 1. And now writing the addition and multiplication tables, 0 plus 0 is 0, 0 plus 1 is 1, 0 plus x is x, 0 plus x plus 1 is x plus 1, 1 plus 0 is 1, 1 plus 1 is 2, which is 0, 1 plus x is x plus 1, 1 plus x plus 1 is x, x plus 0 is x, x plus 1 is x plus 1, x plus x is 2x, which is 0, x plus 1 is 1, x plus 1 plus 0 is x plus 1, and then x, 1, and finally 0. Alright, so now for the multiplication table, once again 0 times anything is going to be 0 here, so I can fill in that first row. Then 1 times anything is going to be that anything, so we've got that second row there. X times 0 is 0, x times 1 is x times x squared is x squared. In this ring you can check that that's going to be congruent to x plus 1. And multiplying x times x plus 1, you can check that this is congruent to 1. Here we get 0, x plus 1, 1, and x. So now, for seeing if this ring is a field, we can check that, okay, we've got a multiplicative identity, which is 1. Next, we've got multiplication is commutative, since our multiplication table is symmetric. And then every non-zero element has a multiplicative inverse. We can also see that from the table. So we can see that because if we multiply 1 times 1, we get 1, so 1 is 1's multiplicative inverse as usual. If we multiply x times x plus 1, we get 1, and in the other order we get 1 as well, so those are multiplicative inverses for each other. And then finally, 1 is not equal to 0 is the last property we need for this to be a field. So yes, it is a field. Yay! Alright. And how many elements does this have? Once again, this has 4 elements. So here we've got a field with 4 elements. So now a question is, in general, how many elements does z mod p adjoin x mod m of x have, where d is the degree of our polynomial m of x? So we saw that over z mod 2, when we were looking at a degree 2 polynomial, we had 4 elements. So the way we can kind of count how many elements we have is by first considering that every polynomial is congruent to a polynomial of degree less than d. And next up, there are p choices for each coefficient. And if we look at a polynomial of degree less than d, we can write that as a0 plus a1x plus a2x plus up through a d minus 1 x to the d minus 1. This has d coefficients once we make sure we count that 0th coefficient or constant coefficient. So notice that then the number of polynomials of degree less than d over z mod p, since we've got p choices for each coefficient and there are d coefficients, then the order of this field is going to be p to the d. And that's consistent with what we saw where we had a degree 2 polynomial over z mod 2. We got 4, which is 2 squared. So now we'll give our big result for when f adjoin x mod m of x is a field. And so it's true that this is a field if and only if that polynomial m of x is irreducible. So if we go back to our examples here, x squared plus x plus 1, that's an irreducible polynomial in z mod 2 adjoin x. and so we saw that that was a field there. And if we look at x squared, that polynomial is not irreducible in z mod 2 adjoin x, so we saw there that that one was not a field. So we have this criterion for figuring out if f adjoin x mod m of x is a field or not. The very rough idea of the proof is that irreducible is analogous to an integer being prime. And so then the proof is going to be very similar to the proof that z mod p is a field when p is prime. So we won't go over this proof in detail. In the group work on Wednesday, you'll go over one part of this proof, or prove one part of, or one direction for the if and only if. So you'll get some part of the proof at least, but we won't cover the whole proof. All right, so we have that if p is prime and m of x is an irreducible polynomial of degree d in z mod p adjoin x, so then z mod p is a field. And if m of x is irreducible, then z mod p adjoin x mod m of x, that's also a field by our previous theorem. So based on how we counted elements, this is going to be a finite field with p to the d elements. And then we have special notation for this field, so we don't have to write that big old long thing all the time. We denote this field by this blackboard bold f sub q, where q is, p to the d, not n. So q is p to the d. So notice that there's some ambiguity in the definition of fq, because there are different irreducible polynomials of degree d that we could choose, which will give us fields that look a little bit different. But all fields of order q are essentially the same. So what this means is something that we aren't covering in our class. If you've had abstract algebra, they're isomorphic, and that's something that would be proved in an abstract algebra class. But all you need to know here is that we don't really need to worry about that ambiguity from our choice of an irreducible polynomial. That it does work out and the field would have the same structure. And another note here, if q is not a power of a prime, so if we're talking about fq and trying to say that for some composite like 6, say, then there is no field with q elements. So there's no field with 6 elements. It's only for powers of primes. So that's something to remember, that we can only write fq when q is a power of a prime number. All right, so that's it for this pre-lecture. So answer those questions, and we'll see you in class.